In this video, we're going to continue working with the law of sines. Previously, you practiced using the law of sines to solve non-right triangles when you know an angle and its corresponding or opposite side. In the cases that you've done so far, you always knew two angles and one side. So we're going to look at what happens now if you're given two sides and one opposite angle. So you're still given an opposite angle and its corresponding side, but something interesting happens here. And there are three possible ways three possible things that can happen. So we're going to take a look at those possibilities here. So the first possibility in this top sketch, I've been given side A and side B and angle A, which is across from side A. But if you look at this, side A is too short for angle A in order to reach down to this horizontal line segment. So there's no possible solution given those three values. Let me just move that mouse cursor out of the way here a second. Okay, so in this case, there's no solution. And really, in this, the way it's drawn here, sketched here, you can see that it's because side A is too short. In the second example, you can see that side A is long enough. We've created a triangle, and now we have an angle and its corresponding side. So we could use law of sines to solve for the rest of the triangle, and we would get one solution. In the third example, further down here, what happens is that we've got this, we could have possibly side A creating a triangle like that, but with the same length of line segment, we might create that triangle instead. And so this is called the ambiguous case because we might have no solution, one solution, or possibly even two solutions, where with the information we're given, there are two different possible triangles. One where angle B here is, in this case, quite a large obtuse angle, and the other one here where angle B would be a smaller angle. So let's look at a couple of examples so that we can see what to look for and how this might work out. Make sure that if you have had your calculator in radian mode, that now you've got it in degrees mode again, because we'll be working with degrees here. So these are the three pieces of information I've been given. Two sides, A and B, are 10 and 40 units, and angle A is 30 degrees. So just sketch a triangle. It does not need to be drawn to scale, but I've got A, B, and C, and I'm going to just switch those around and go the other way around. So let me just redraw that. Oops. A equals 10. So I've got A, B, and C. Angle A is 30 degrees. There's side C. Side A is 10 and side B is 40. And again, this is not drawn to scale at all. So because we have this corresponding pair, we can use the law of sines, and we've got side B, so we'll use it to try to find the sine of B, or angle B. Okay, so sine of B over 40, and I always put my unknown top left of the proportion. It just makes it always very consistent as to how you solve the rest of the equation. Will be equal to the sine of 30 over 10. So if I rearrange that, I will have sine of B equals 40 times the sine of 30 divided by 10, which will give me that the sine of B equals 2. If you do the inverse sine on this to find the angle, you'll get an error message because sine is never greater than 1. Okay, so this is impossible, and so this is an impossible triangle. Okay, that means that if I had a side 10 and a side 40 and an angle 30 in this configuration, I would not be able to actually draw a triangle. I look at the second example. I've got side A is 30, B is 20, and angle A is 50. So I'm just going to draw triangle again, 50 degrees, A, B, and C, where side A is 30 and side B is 20. Okay, so again, I've got a corresponding pair. I've got the 50 degrees corresponding with side 30, so now I'll use that 20 corresponding with angle B to solve for angle B. So the sine of B over 20 will be equal to the sine of 50 over 30. And if I use my calculator, I'll get sine B equals 0.5107. And that's a reasonable estimate for, or a reasonable number for B, a sine, because it's always between -1 and 1. It's important to remember with your knowledge of the unit circle and angles in standard position that there can possibly be two angles that have this sign. Your calculator will give you as the sine inverse of, or the inverse sine of 0.5107. It'll give you 31 degrees. Your calculator is always going to give you the acute angle that has that sign. So 31 degrees has that sign. But from your knowledge of the unit circle, you know that whatever angle has that reference angle of 31 degrees will also be 0.5107, and that happens to be 149 degrees. We take the 180 and subtract 31 to get 149 degrees. So we solve this by taking one of the angles at a time, and always start with the first angle that you got, okay? So we have angle B being 31 degrees, and let's solve the rest of the triangle doing that, okay? So if angle B equals 31 degrees, okay, then angle C will be 180 minus the 50 degrees of angle A minus the 31 degrees of angle B, and we'll get angle C equals 99 degrees. So now to get side C, we can say that C over the sine of 99 degrees is equal to 30 over sine 50. So we'll rearrange that equation, multiply both sides by sine 99, and we get that C is 38.7 units long. Okay, so that works quite nicely. Let's take a look at what happens if we try the second angle we got, the 149 degrees. If angle B equals 149 degrees, then what does angle C going to be? It's going to be 180 minus the 50 for angle A minus 149, which gives us -19 degrees. Well, that's not possible to have a negative angle in a triangle. So there's only one solution. And that's the solution that we already have, giving angle C and side C as shown above, where angle C is 99 degrees and side C is 38.7 units. So now let's look at a third example where side A is 30, side B is 40, and angle A is 20. Okay, so again, we have a corresponding pair here, so we can use the 40 to find angle B. So the sine of B over 40 will be equal to the sine of 20 over 30. And we'll rearrange that with our calculators and get sine of B equals 0.4560. So again, we'll use the inverse sine. And we'll get that B is 27 degrees. But again, that is the acute angle, but sine being positive in quadrant 2 as well means that we've got another angle at, that will have the same sign, and that angle will be 180 minus 27. So angle B could also be 153 degrees. So again, start with the acute angle that we're given, and let's use that to solve for angle C and side C. So if B is 27 degrees, angle C will be 180 minus the 20 of angle A and minus the 27 of angle B, and angle C then is 133 degrees. We can use that now to find side C, so side C over the sine of 133 equals 30 over sine 20. Notice that I always go back to the original values that I was given to solve for a missing number, if rather than going to a calculated number. You're less likely to have errors of rounding and errors in general if that's what you do. And so when I do some rearranging here, I get that side C is 64.2 units. So I've solved the triangle using B equals 27 degrees. Now, let's see what happens with the second angle. We got B is 153 degrees, so then angle C will be 180 minus the 20 for A that we were given, minus 153 degrees. And we get angle C is 7 degrees. So then we can solve for side C. C over the sine of 7 is equal to 30 over the sine of 20. And we do some rearranging and we get that C equals 10.7. So this case, because angle C made sense, we can get the angles, the three angles adding up to 180 degrees with this second value for angle C. We get a second possible value for side C as well. So there are two triangles that have the criteria for that we were given. Okay, so if I were to make a little sketch of those, I'm going to just try to do this roughly here. Okay, so in this case, A is 30, B is 40, and C is 64.2, and angle C is 133. Okay, in the second case, oops, I need to make that smaller. I've got my ABC, and B is 40, A is 30, C is only 10.7, and angle C is only 7 degrees. Okay? And that's it for the law of sines.